Welcome back to this lecture series on deep learning. In today's session, we'll explore one of the most fundamental topics that form the backbone of deep learning and machine learning, that is called linear algebra. We'll start by understanding the key elements, that is scalars, vectors, matrices, and tensors, which are essential to represent and manipulate data in machine learning models. Whether we are feeding input into the neural network, calculating weight updates, or transforming data between layers, these mathematical structures are always involved. So let's begin this lecture by breaking down each of these components and seeing how they connect to deep learning systems. We'll see one by one. First, introduction. The linear algebra. Linear algebra is the core mathematical language of AI. Linear algebra serves as the fundamental mathematical framework underlying artificial intelligence. Every operation in machine learning and deep learning, from input transformation to parameter updates, relies on algebraic structures such as vectors and matrices. In AI systems, data is typically represented as scalars, vectors, matrices, or tensors, depending on the complexity and dimensionality of the problem. These formats allow efficient storage, access, and computation. Next, these structures are essential in neural networks for organizing weights, inputs, and intermediate computations. Their mathematical properties enable scalable and parallel processing of large data sets. First, we'll see scalars. A scalar refers to a single numerical value and represents the simplest unit in linear algebra. It can be any real number. And the scalars are typically denoted as using the, that is lowercase a, inclusive of r, and it represents the set of real numbers. Say, for example, if you are taking examples of scalars include values like a is equal to 7 and lambda is equal to minus 3.5, which may be correspond to learning rates, thresholds, or singular measurements. And the scalars are magnitude only quantities and do not include any notation of direction, making them ideal for expressing constants or scaling factors. Next, vectors. A vector is defined as, there is 1D vector, one dimensional, is defined as an ordered array of scalars. Each element in the vector holds a specific value and position, making the sequence meaningful. And vectors are typically denoted as vector v is equal to inclusive of r to the power n, indicating a real valued vector of dimension n. Here this n represents the dimension. The column vector format is given by v is equal to v1, v2 up to vn. N is the dimension. It is commonly used in matrix manipulation and machine learning pipelines. And the row vector form is written as v to the power v transpose is given as v1, v2 up to vn, and typically the transpose of the column vector. Next, the norm. Here, double straight line. It represents the norm or magnitude of a vector and is calculated using root of v1 square, v plus v2 square plus v3 square, etc. plus vn square, and gives the Euclidean length of the vector in a space. Next, vector operations. Vector addition is performed element wise. Two vectors of equal length are added by summing corresponding entries. A plus b is equal to, here if we have the vector a is containing a1, a2 up to an, b is containing b1, b2, b3 up to bn, we can add like this: a1 plus a2 and a2 plus, it will be added and it will be forming in the matrix format and result in a scalar, often used to determine similarity or projection. Next, a unit vector, the dot product a dot b is given as between two vector is calculated as a dot b is equal to a1 b1 plus a2 b2, and it is also measured to find out the similarity. and projection. This scalar multiplication alpha v. This is the scalar multiplication. This is the dot product. And a unit vector here. Unit vector is created by normalizing a vector v divided by normalization of the vector v, which keeps direction and adjusts its length to 1. Next matrix is a matrix is a two-dimensional array of scalars arranged in rows and columns. It generalizes vectors by adding another axis of organization, and matrices are typically represented as A inclusive of r to the power m cross n, and this m cross n meaning that dimension, meaning the matrix has m rows and n columns. Say for example, A is given at as 1 2 3 4 5. How many rows are there in this? 2 rows. And how many columns are there? 1 2 3. So two rows and 3 columns. And each row in a matrix can be viewed as an individual feature vector, which facilitates row-wise operations and data batching. Next, matrix operations. Matrix addition is done element-wise, where corresponding entries of two matrices of the same shape are added together. Scalar multiplication of matrix involves multiplying each entry by the scalar value, maintaining the original matrix shape. And matrix manipulation follows the rule where the dot product is computed between rows of the first matrix and column of the second. Next, the transpose of matrix A transpose, that is Ij. It flips its rows and columns, which is often used in reshaping data for compatibility and during operations such as dot products or back propagation. Next, special matrices, or these are all the special matrices. Identity matrix. The identity matrix I is given it as it has 1 0 0 0 1 0 0 0. Here diagonal we will have 1. This value, the identity matrix, has a 1 along its diagonal and zeros elsewhere. It acts as multiplicative identity for matrix products. The zero matrix consists of entirely of zeros. Any matrix multiplied by zero matrix results in another 0. Here 0 0 0. And diagonal matrix, see here d1 d2 d3. Here instead of having 1, 1 means that is identity matrix, we'll have some values 1 2 3 4 or -4 -5 etc. A diagonal matrix has all non-diagonal entries as 0. Here 0. Each diagonal entry scales the corresponding dimension in a vector space independently. Next, tensor. A tensor is a multi-dimensional generalization of vectors, and vector 0-dimensional, 1-dimensional, and matrices in 2-dimensional. It can have 3 or more dimensions. Tensors are classified by rank, which refers to the number of dimensions. For example, rank 3 tensor could represent a color image weight with height, width, and a channel. The notation is given by tensor is equivalent of r to the power t1, t2 up to into dn. It specifies a tensor with the n axis where each axis has a given dimension. An example of 3D tensor is image data in shape is given by h, w, c, height, weight, where h is the weight, w is the width, c is the number of color channels, RGB, we can say red, green, blue, like that. Next, linear how the linear algebra is used in next, shape and rank. The shape of a tensor is described by described by the tuple of its dimension, such as see here d1, d2, d3, and here the rank of the tensor is number of dimension it has. For example, a vector has rank 1, matrix has rank 2, and image patch tensor might have rank 4. Next, linear algebra in deep learning. Input data is given by x belongs to r to the power n. N is the dimension, all you know that. It's typically represented as a vector containing features like pixel values, sensor readings, or word embeddings. And here the weight is given by neural networks are stored as matrices. W belongs to r to the power m cross n. M cross n or the matrices. Number of neurons, that is M is the number of neurons and N is the number of input features. The output layer is computed using y is equal to wx plus b, where here w, you know that weight, input x is the input, b is the bias. Backpropagation and training involves computing derivations of the loss function with respect to weight and inputs, which are also expressed as matrices and vectors. Every layer in deep learning model process data in the form of tensors, making tensors algebra essential for both forward and backward processes. So coming into the summary, this session has highlighted the coming into the conclusion. This session has highlighted the foundational role of linear algebra in deep learning, focusing on scalars, vectors, matrices, and tensors. These structures form the basic units through which data is represented, manipulated, and processed in neural networks. Scalars hold single values, vectors represent features, matrices handle multidimensional relationships, and tensors extend to higher dimensions for complex data like images and videos. A solid understanding of these elements is essential for grasping how deep learning models function. Hope everyone understood the topic. Thank you for your passion listening, and I hope you enjoyed learning. Thank you once again.